Imagine the profound silence of the cosmos, stretching across light years of unimaginable emptiness. Then, shattering that stillness, a cosmic bullet tears through the void. On the night of July 1st, 2025, astronomers operating the vigilant ATLAS telescope high in the Chilean Andes locked onto something utterly unexpected. A minuscule gliding speck of light positioned just beyond the mighty orbit of Jupiter. In those initial breathless moments, it seemed mundane, perhaps just another anonymous asteroid or a local comet tracing its ancient path around our sun. But within mere hours, a chilling realization swept through the global astronomical community like an electric shock. This was no ordinary denizen of our solar backyard. They were witnessing something profoundly alien, a comet born not under our sun, but forged in the unimaginable cold and distance of interstellar space, a true wanderer from the stars. Now christened Comet 3 I/ATLAS. This frozen voyager from the abyss is only the third such interstellar object ever confirmed to breach our celestial shores. And in the stunningly short span of days following its detection, it has detonated into a global astronomical obsession, a cosmic bombshell gripping scientists and stargazers alike. This unprecedented visitor holds the electrifying potential to unravel the maddening enigmas left in the wake of its two cryptic predecessors, the utterly bizarre Oumuamua and the strangely familiar comet Borisov. The sheer possibility is mind-blowing, but the immediate critical question blazed. How do we know, beyond any shadow of a doubt, that 3I/ATLAS is an interstellar invader? The undeniable fingerprint lies in its terrifying breakneck motion. Picture the graceful elliptical dances performed by comets, asteroids, and planets within our solar system, their speeds perfectly choreographed by the sun's immense gravitational embrace. Now, contrast that with 3I/ATLAS. It is hurtling through our neighborhood at a velocity so staggering it defies belief, approximately 70 kilometers per second. Relative to our sun, to grasp the sheer insanity of this speed, understand that it far, far exceeds the solar system's escape velocity at its current location. An object traveling this fast cannot possibly be shackled by the sun's gravity. It is merely slingshotting past us, a cosmic ghost passing through. Its trajectory isn't elliptical. It's brutally, mathematically hyperbolic. Orbital eccentricity is the key metric here. A perfect circle scores 0. An ellipse falls between 0 and 1. And a parabolic escape route is exactly 1. Anything screaming above 1 is hyperbolic, screaming interstellar. 3. I/ATLAS doesn't just nudge above. It smashes the scale with a current eccentricity estimated above a staggering 6. This isn't just a sign. It's a cosmic siren wailing its interstellar origin. A velocity so extreme, it chills the blood of anyone comprehending the forces involved. So, it's interstellar, a fact both terrifying and exhilarating. But the next heart-pounding question arises. How can we be certain it's a comet? Classifying 3 I/ATLAS as a comet means it isn't merely a desiccated, inert boulder rocketing through the eternal night. No, this implies it's an icy entity, a volatile snowball reacting viscerally to the sun's warming touch. As the sun's rays penetrate its frigid exterior, volatile ices trapped deep within begin their explosive transformation, sublimating directly from solid to gas, erupting in jets that blast dust and vapor into space, forming the telltale coma, a hazy shroud, and potentially, spectacularly, a tail streaming millions of kilometers behind it. Those initial nerve-wracking observations of 3I/ATLAS revealed a critical clue, a faint, ghostly fuzziness enveloping the pinpoint core of the object. This ethereal halo was the smoking gun, the first visual whisper of cometary activity stirring. Within a frantic, adrenaline-fueled 48 hours, over 100 follow-up observations pouring in from observatories scattered across the globe confirmed tentative but undeniable signs of a developing coma and the nascent emergence of a short, faint tail. These are the unmistakable birth pangs of a comet awakening, beginning to shed its frozen essence as it plunges ever closer to the solar furnace. The response was swift and definitive. The International Astronomical Union, acting with unprecedented speed, formally updated its classification to C/2025 N1ATLAS, officially recognizing its active, volatile, and undeniably icy nature. The name itself is a coded message from the cosmos, following the strict standardized naming convention dictated by the IAU for these celestial newborns. Each segment of this celestial designation reveals a vital piece of the puzzle. The prefix "cool" is absolutely crucial. It loudly proclaims that this object is a non-periodic comet. It screams to the universe that it is not a regular visitor bound by the clockwork mechanics of our solar system. It is a one-time apparition, a fleeting ghost destined never to return. The number is 2025. And simply, yet profoundly, denotes the year of its discovery, forever anchoring it to this moment in human history. Finally, we arrive at the letter number combination N1. This seemingly innocuous code breaks down into two deeply revealing components. The letter N pinpoints the specific half-month window of discovery. The IAU ingeniously slices each year into 24 precise half-month intervals. A signifies the first half of January, B the second half, marching sequentially through the alphabet. The letter N corresponds with meticulous accuracy to the first half of July, a detail made possible because the letter I is deliberately omitted to prevent any catastrophic confusion with the number 1. Therefore, N1 translates with cosmic finality to the first non-periodic comet discovered in that specific first half of July 2025. It is literally the first of its kind in that temporal slice, a unique identifier for this interstellar vagabond. Further bolstering its cometary credentials is the object's evolving brightness. While brightness alone isn't a direct measure of the nucleus size, a deceptive factor because the ejected dust cloud acts like a giant light-reflecting halo. Its increase is a screaming indicator of surging activity, of volatile ices vaporizing furiously under the intensifying solar glare. Current estimates, refined rapidly with each passing night of observation, place its nucleus size anywhere from a substantial 5 kilometers to a truly colossal 50 kilometers in diameter. If confirmed towards the upper end, this would instantly crown 3I/ATLAS as the largest interstellar object ever observed by human eyes, dwarfing its predecessors and adding another layer of jaw-dropping significance to its passage. At the electrifying moment of its discovery, 3I/ATLAS was a staggering 670 million kilometers distant from Earth, having just breached the orbital realm dominated by Jupiter. Its light, piercing the void, was incredibly faint, approximately 2.5 million times dimmer than the steadfast North Star Polaris, a true cosmic needle in the haystack, requiring the sharpest eyes of modern technology to detect. The comet's trajectory is now mapped with increasing precision, painting a picture of its perilous journey inward. Comet 3I/ATLAS is predicted to reach its Bixto perihelion, the white-hot point of closest approach to the Sun, the moment of maximum stress and maximum spectacle, around October 30th, 2025. At this critical juncture, it will skim the Sun at a distance of roughly 206 million kilometers. To provide context, this places it just inside the orbit of Mars, deep within the inner solar system furnace. However, in a cruel twist of celestial geometry, during this pivotal, fiery climax, 3I/ATLAS will be positioned almost directly behind the Sun as viewed from Earth. This solar conjunction presents a formidable, agonizing barrier, severely limiting our ability to directly observe the comet at its most active, potentially explosive phase. It's like having front-row seats to a cosmic supernova, only to have the curtain fall at the crucial moment. Astronomers worldwide are already strategizing, deploying every conceivable tool to pierce the solar glare. But the challenge is monumental. The next window of opportunity cracks open in early December 2025. As 3I/ATLAS swings out from behind the sun's blinding corona, it will reappear in our pre-dawn or post-dusk skies, presenting a second, vital chance for observation. This is the critical period to study the aftermath of its solar encounter, the state of its nucleus, the composition of its coma, the structure of its tail. It will likely remain visible, a fading cosmic ember, to the world's largest and most powerful ground-based telescopes until perhaps early 2026, a precious few months to gather as much data as possible before it dwindles, fades, and vanishes irrevocably back into the infinite, lightless depths of interstellar space, lost to us forever. The urgency is palpable, the countdown relentless. To grasp the truly earth-shattering significance of 3I/ATLAS, we must rewind to the fleeting, mind-bending encounters with the only two confirmed interstellar objects that preceded it. Encounters that left astronomers reeling with more questions than answers, and whose legacies 3I/ATLAS might finally resolve. The first was the now legendary Oumuamua 1I/2017 U1. Discovered in October 2017, its trajectory was unmistakably terrifyingly interstellar, a fact that alone sent shockwaves through science. But what truly plunged scientists into a vortex of confusion and frenzied speculation was its utterly inexplicable behavior. Justice. After it whipped around the sun. Unlike any natural space rock ever observed, Oumuamua didn't just follow the elegant curve dictated purely by gravity. No, it exhibited a slight, yet meticulously measured and utterly inexplicable acceleration, as if an unseen hand was gently, persistently pushing it away from the sun. This phenomenon, termed non-gravitational acceleration, is typically the signature of outgassing, jets of vapor erupting like microscopic geysers from a comet's heated surface. But here was the maddening twist. Oumuamua displayed absolutely zero visible signs of such activity. No coma, no tail, no dusty shroud, nothing. It presented as a stark, bare, dark object, adding profound fuel to the firestorm of mystery. The way its brightness flickered and pulsed over time suggested it wasn't just tumbling, but spinning in a complex manner, and crucially, that it possessed an extreme, unprecedented shape, wildly elongated like a cosmic cigar, or perhaps unnervingly flat like a celestial pancake, a shape utterly alien to our solar system's catalog of asteroids and comets. These bizarre characteristics ignited a supernova of theories. Some scientists proposed exotic ices, like frozen hydrogen or nitrogen, sublimating so cleanly they left no visible dusty trace, a concept pushing the boundaries of known physics. Others, more controversially, and capturing global headlines with terrifying implications, dared to speculate it could be artificial, perhaps a derelict light sail from an advanced extraterrestrial civilization, a haunting artifact drifting through the void. While the idea of an alien artifact ignited the public imagination, the scientific community has, through rigorous analysis and Occam's razor, largely ruled it out. The consensus now leans heavily towards Oumuamua being a natural object, albeit one of a type we've never encountered before, and whose exact composition, structure, and violent origin story remain deeply shrouded in frustrating, provocative mystery. It was, and remains, a cosmic Rorschach test. Then came 2I/Borisov, C 2019 Q4. Discovered in 2019 by the keen-eyed amateur astronomer Gennady Borisov. In stark, almost comforting contrast to Oumuamua's unnerving strangeness, Borisov looked and behaved precisely like a textbook comet hailing from our own Oort cloud. It burst onto the scene with a brilliant, unmistakable coma and developed a long, majestic, dusty tail that stretched spectacularly across telescopic fields of view. Spectroscopic analysis confirmed the presence of familiar carbon monoxide, cyanide, and water ice, the very building blocks we associate with solar system comets. Its appearance was a profound relief to many astronomers, validating long-held theoretical predictions about what a typical interstellar comet should resemble. Crucially, Borisov delivered the electrifying proof that our solar system isn't unique. Other star systems also manufacture these volatile icy bodies and can, through gravitational upheavals, violently eject them into the interstellar void, capable of surviving the eons-long journey. Borisov was the familiar stranger. Together, the hauntingly bizarre Oumuamua and the reassuringly familiar Borisov presented astronomers with a stunning revelation. Interstellar objects are not a monolithic class. They can be wildly, astonishingly diverse, ranging from dark, rocky, silent enigmas to brilliantly active, icy spectacles that mirror our own cometary family. This diversity is both thrilling and deeply challenging. And now, hurtling into our view, comes 3I/ATLAS. This is our third precious data point, a gift from the cosmos arriving at the perfect moment. It is absolutely crucial, potentially the key that unlocks which of these types, the bizarrely inert or the actively volatile, represents the norm for interstellar travelers and which is the terrifying or comforting outlier. 3. I/ATLAS isn't just another comet. It's the potential Rosetta Stone for deciphering the nature of matter ejected from other solar systems. The timing of 3I/ATLAS's arrival is nothing short of cosmically fortuitous. We stand on the precipice of a revolution in our ability to detect and study such fleeting visitors. Global sky survey capabilities have undergone quantum leaps since Borisov's visit just 6 years prior. Networks of automated telescopes like ATLAS, Pan-STARRS, and the Catalina Sky Survey now continuously scan vast swathes of the heavens, their electronic eyes far sharper and faster than ever before. Astronomers, armed with more powerful instruments, faster computers, and refined detection algorithms, are poised and primed, ready to dissect 3I/ATLAS in ways unimaginable during the previous encounters. This icy messenger from the stars could hold the answers to the maddening, persistent questions raised by the ghostly passage of Oumuamua, its very nature, displaying clear, unambiguous signs of cometary activity with a visible coma and tail, stands in stark, almost defiant contrast to Oumuamua's eerie silence and barren appearance. If 3I/ATLAS continues to behave like a typical active comet as it dives towards perihelion, outgassing predictably, following standard orbital models, exhibiting familiar chemistry, it would powerfully suggest that Oumuamua was the profound anomaly. Perhaps Oumuamua was a freak fragment, shorn from a larger body in a cataclysmic collision long ago, its volatiles long spent. Maybe it was a unique type of ultra-dense, rocky, icy hybrid, sculpted by eons of brutal interstellar radiation into its impossible shape. Its ice is buried too deep, or of a type that sublimates without dust. 3I/ATLAS. Acting normally would relegate Oumuamua to the status of a fascinating cosmic oddity, not the terrifying herald of a new paradigm. Conversely, and the thought sends shivers down the spine, if 3I/ATLAS begins to exhibit strange, unexplainable phenomena as it nears the sun, sudden anomalous accelerations not accounted for by outgassing, like Oumuamua's, but perhaps more pronounced. Bizarre chemical signatures utterly alien to our solar system comets, or unexpected changes in rotation or outbursts. It would throw the door wide open. It could mean that Oumuamua wasn't strange enough, or that our understanding of comet physics is fundamentally incomplete. It might hint that interstellar spacecrafts objects in ways we haven't begun to fathom, or that planetary systems out there produce comets with radically different properties. The stakes are cosmically high. Furthermore, the spectroscopic fingerprints of 3I/ATLAS will be scrutinized down to the last photon. by meticulously comparing the ratios of its detected molecules, water, carbon monoxide, carbon dioxide, cyanogen, complex organics, to those found in Borisov, and, crucially, in our own solar system comets, scientists can perform a revolutionary experiment. They can directly test whether the fundamental chemistry of planet formation, the freezing points, the abundances of elements, the processes that build icy planetesimals, is a universal constant throughout the galaxy, or if each stellar nursery cooks up its own unique, localized blend of cosmic ingredients. Does the universe follow a standard recipe for cometary ice, or is every star system a distinct kitchen? This isn't abstract astrophysics. This is direct, tangible insight into the processes that build planets around other stars, processes that might have led to Earth-like worlds, or something unimaginably different. Comet 3 I/ATLAS, this frozen archive from another sun, carries that encoded information within its evaporating ices. Every jet, every molecule released is a page from another solar system's history book, now being read under our sun's light for the first time. The potential discoveries locked within its spectral lines are literally mind-blowing. While Comet 3 I/ATLAS may be only the third interstellar object ever confirmed, its arrival heralds a dawn where such discoveries could become breathtakingly frequent. The key to unlocking this torrent of interstellar visitors lies in a revolutionary new sentinel, now nearing completion, high in the Chilean Andes, the Vera C. Rubin Observatory. Rubin isn't just another telescope. It represents a quantum leap, a paradigm shift in our ability to survey the dynamic sky. Its centerpiece is a truly monstrous 3.2 gigapixel camera, the largest digital camera ever constructed for astronomy, coupled with a mirror designed for an unprecedented wide field of view. This combination allows Rubin to perform an almost unimaginable feat. It will image the entire available night sky, not once a month, not once a week, but comprehensively every 3 to 4 nights. This relentless, all-seeing cadence is a game-changer. It means Rubin can catch transient, fast-moving objects like interstellar comets or asteroids much earlier in their approach, when they are brighter and observable for longer periods. It dramatically increases the probability of spotting these faint, high-speed interlopers before they zip past and vanish. The power of Rubin isn't theoretical. During its limited first-look commissioning phase earlier this year, a mere taste of its capabilities, the observatory astounded the world by identifying over 2,000 previously unknown asteroids within just a few hours of operation. When Rubin becomes fully operational in late 2026 or early 2027, it is projected to utterly transform solar system astronomy. The discovery rate for near-Earth asteroids, Kuiper Belt objects, and, critically, interstellar objects, is expected to skyrocket. Instead of waiting with bated breath for years or even decades between these cosmic visitors, scientists now realistically anticipate detecting multiple interstellar objects every single decade, perhaps even several per year, once Rubin hits its stride. This isn't incremental progress. It's an explosion of discovery waiting to happen. This impending flood of data is absolutely vital. Currently, with only 3 confirmed ISOs, and one of those, Oumuamua, remains deeply perplexing. Astronomers are trying to decipher the grand narrative of galactic planetary formation with a ridiculously tiny, statistically insignificant sample size. It's like trying to understand all of Earth's biodiversity by examining 3 random insects: 1 beetle, 1 butterfly, and 1 utterly unknown, unclassifiable bug. The conclusions drawn are inherently fragile, prone to being overturned by the next discovery. Rubin promises to change this fundamentally. With potentially dozens of interstellar objects identified and characterized over the coming decade or two, astronomers will finally be able to categorize them robustly. They'll trace their likely origins back to specific regions of the galaxy by analyzing their incoming trajectories. They'll build statistically sound models of their sizes, compositions, activity levels, and structures. This comprehensive census will forge a radically deeper understanding of how planets and comets form in other solar systems, and, crucially, the violent gravitational dynamics, planetary migrations, stellar flybys, the death throes of stars, that can rip these objects from their birth systems and fling them across the galaxy at terrifying speeds. Each ISO is a fossilized messenger from a specific moment in another system's history. Rubin will provide the population study needed to read the galactic story they collectively tell. The Vera C. Rubin Observatory isn't just a telescope. It's a gateway to understanding our place in a galaxy teeming with ejected worlds and icy wanderers. As Comet 3 I/ATLAS streaks through the inner solar system over the coming months, an unprecedented global campaign of observation will track its every move. The world's most powerful ground-based telescopes, Keck, Gemini, the VLT, Subaru, will train their immense light-gathering eyes upon it. Space-based assets like the James Webb Space Telescope, JWST, Hubble, HST, and even planetary missions capable of pointing their cameras outward will join the vigil. JWST in particular holds immense promise, its infrared gaze capable of piercing the comet's dusty coma to probe the chemical composition of the nucleus itself and the gases sublimating closest to it, potentially revealing complex organic molecules. Spectroscopy will be paramount, breaking down the comet's light into its constituent colors to identify the fingerprints of molecules. Photometry will meticulously track its brightness variations, revealing rotation rates and outbursts. Radar observations, though challenging due to distance and speed, may be attempted to directly probe the nucleus shape and surface properties. Every photon captured is precious data. Astronomers will be watching with a mix of intense anticipation and nervous vigilance, hoping this third visitor will unlock secrets the first two only hinted at or fiercely guarded. Will it confirm Borisov's familiar nature? Will it solve the Oumuamua riddle? Or will it present something entirely new, forcing yet another rewrite of the textbooks? The next few months are a high-stakes race against time as the comet plunges sunward, reaches its fiery climax, and then begins its long, irreversible fade into interstellar night. We stand at a pivotal moment in cosmic exploration. Thanks to exponentially better tools, automated surveys, larger telescopes, vastly more sensitive instruments, sophisticated data processing, and the imminent revolution promised by the Vera Rubin Observatory, we are now better equipped than ever before in human history, not just to spot these interstellar messengers, but to study them in profound detail. Missions specifically designed to intercept future, more accessible ISOs are moving from science fiction into serious feasibility studies within agencies like NASA and ESA. The dream of catching up to one, flying alongside it, perhaps even sampling its primordial material, no longer seems impossible, merely incredibly challenging. Comet 3 I/ATLAS is a harbinger. Its passage is a stark, beautiful reminder that our solar system is not an isolated island. We are part of a